Swayam Prabha. Digital India. Educated India.
So, we are going to be looking at energy balance today. What we are trying to do here is look at energy balance for a stirred vessel. Now, stirred vessel in which there is a stirrer where the composition of the system is uniform at different positions, or say the intensive properties of the system is the same everywhere because of the mixing that you have introduced. You have Fj moles coming in, Fj0 moles coming in, Fj moles going out. You have so much of heat coming in, so much of work coming out. The system itself has Ni moles of component I, each of energy Ei, and the energy of the system we denote as E system. Okay. And statement of energy balance is that input minus of output plus generation is accumulation. What we recognize here is that in energy balance there is no generation of energy or destruction of energy, therefore, generation term should not appear, unlike in the material balance where we accept that there is generation of material because it can form another product. Therefore, this term is removed. So, the statement of energy balance is simply input minus of output equal to accumulation. Stating this in mathematical representation is d by dt of E system equal to sigma 1 to n E I F I input and then E I F I output summed over all species plus Q minus W S. Okay, where Q is heat input, W is work output. This is the energy that is coming in with all the species, energy that is going out with all the species. We are neglecting heat of mixing, that is neglected here. We will include if required at a later stage. E I is the energy content of each of the species, and this consists of kinetic, this is internal energy, kinetic energy, potential energy. Notice that the units of this is joules per kg, or in SI units can be also called as meter squared per second squared. Okay. Now, this term W dot can be understood in some ways by looking at a term called flow work. What is flow work? Flow work is the work that is required to get material in and out of a system in the absence of friction. Something that has to be understood by actually making a calculation of the term Fi Pt omega I. Now, Fi Pt omega I in the absence of chemical reaction does not change. Okay. But Pt omega I can change depending upon the conditions under which your system is working, high pressure, low pressure, whatever. So, in a sense Pt Fi Pt omega I, which is the units of joules per second or watts, this really depends upon the reacting system. Therefore, this difference between Fi Pt omega I out minus Fi Pt omega I in, this can be positive, it can be negative. If it is negative, it means what? This amount of work has to be put into the system, so that the material can be put in and taken out. So, energy that is required to put material in and out of the system is what is flow work in the absence of friction. So, we can understand the total amount of work that comes out of the system W in terms of shaft work, which we can measure. Shaft work we can measure by measuring the amount of generator output and so on, while flow work we cannot measure, but we can calculate because Fi Pt omega I is a known quantity. You can measure, and therefore, these two terms can be, this can be calculated, this can be measured, and therefore, you can calculate W dot. So, keeping this in mind, what we are saying is that if you look at as an example, we make a calculation of how much is the flow work required to put material in and out through a sulfur dioxide plant, for example, say 3000 tons per day sulfur dioxide plant. What is the flow work we are talking about? So, we can calculate a sigma Fi Pt omega I out, Fi Pt omega I in, because we know what is Pt, typically 1 atmospheres, omega I we can calculate, or we can simply say Fi omega I is simply volumetric flow. So, we know how much is the change in volumetric flow at the inlet to outlet. Why does it change? Because temperature has changed. Okay. So, we can actually calculate this whole term, and the estimate of this is what I have got here. The flow work for a plant of this size turns out to be about 125 kilowatt. It is a minus sign indicating that you have to put that amount of work, so that the material can be put in and brought out. But we have done calculation in an earlier class as to the amount of energy that is required in terms of pressure drop. We have calculated that for a 3000 tons per day plant, and we found out this close to about 2.5 megawatts. So, what we are saying here is that even in the absence of friction, you would have to spend 125. In other words, the minimum energy that is required to put material in and out is not 0. This is the point that we have to appreciate when you have to deal with all these numbers. We can also calculate what is the energy that might be associated with expansion of steam through a turbine going from point 1 to point 2. This is a steam turbine cycle producing power, this is producing power. What does it do? We have a boiler which provides energy into steam, and then we have a condenser. So, Q 1 minus of Q 2 is the amount of work that would come out of the system. First law is energy balance, and that comes out partly through this, partly it is used up here. The net work is W t plus W p. This is what comes out Q 1 minus of Q 2. This we know. But what is of interest here is to find out what is the flow work from 1 to 2. So, I have got here what is the pressure, what is the temperature, what is the specific volume. So, we can calculate P t omega I 2 minus P t omega I 1. So, this if you put all the numbers down, you will find that it is about minus 2.63 kilocalories per kg, showing that there is a small amount of work that you have to do to be able to put material in and out, even for a steam turbine. So, what are we saying? Saying is that our statement of energy balance, which is d by dt of E system, which is energy in minus of energy out, plus Q, which is heat input, and this work I have separated the work in terms of shaft work and flow work. This term F I P t omega I out, F I P t omega I in can be appropriately clubbed with the functions in and out. So, when you do that, this equation looks something like this, where E I plus P t omega I in and then E I plus P t omega I out multiplies the appropriate terms. So, E I consists of, which is called as internal energy, kinetic energy and potential energy. So, this E I, if I substitute here, the whole term looks something like this, that the total amount of energy which is in the system, which is E system for example, consists of N I moles. So, I put N I here multiplied by what is the energy? Energy is U I, which is internal energy, kinetic energy, potential energy. You notice here that P t omega I occurs only in the flow term and not in the accumulation term. Therefore, that term is not included there. So, this I have clubbed U I plus P t omega I can be clubbed. We recognize that P t omega I is P v, U plus P v is H. So, it becomes enthalpy plus the kinetic energy and potential energy. So, the energy balance term, when you club all these terms together, it looks something like this: d by dt of N I, the number of moles in the system, multiplied by H I U I squared G Z I minus P t omega I. I put it like that. That means, I put it in terms of H I even on the left hand side, even though H I U I was there, I have called U I as H I minus the P t omega I. On the right hand side term, I have clubbed the U I plus P t omega I as H I in, H I out, so leaving these two terms, which is kinetic energy and potential energy, plus Q minus W s. So, what seems to happen in reacting systems is that these terms are not very important. Generally, these terms are not very important. In other words, by and large, we are dealing with the enthalpy of the materials which we are dealing with. So, a simplified form of the energy balance can be looked up like this. You have d by dt of N I H I, and then you have F I H I in, F I H I out plus Q minus W s. So, this is something we could have written even without having to go through all this, something that we know for a long time. But the point of writing this is to draw your attention to two important features. When we write d by dt of N I H I, okay, we are actually neglecting the effect of P t omega I. We are neglecting the effect of U I squared and G Z I. Okay. So, this is important to recognize, because there could be instances where these are not negligible. So, you must recognize that these assumptions are involved in the simplified representation of the energy balance that is written here. So, that means, on the left hand side N I H I is actually that HI was not there, UI was there, we replaced it by HI. When can we do this? We can do this if UI and HI are not very different, which is often the case as far as reacting systems are concerned in our domain of interest, but it may not be always. So, we have simplified on the left hand side here. On the right hand side, we have neglected kinetic and potential terms, which may not by and large may be right in most cases, but there are situations where they may not be correct. So, just to summarize, what we are saying is that a simplified representation which involves only NiHi on the left hand side and FiHi on the right hand side is a very simplified representation, which will apply for most cases, but may not be for all cases. Just to understand this, let us just look at a hydel turbine. So, what is a hydel turbine? What is a hydel turbine? You have a reservoir which has water, a huge quantity of water. It is available at a certain height h, so that you can use that potential energy to run a turbine. How do you apply your energy balance? What is your energy balance? D by dt of system. So, what we are trying to say here is that when there is a huge amount of energy here and we are drawing a small amount on a daily basis or a hourly basis, the rate at which the energy of the system changes we can neglect under the quasi steady state approximation. That means, if the time scale for which we are observing the system is small in relation to the time scale over which the reservoir gets consumed, the left hand side can be seen as quasi steady, therefore, can be deleted. On the right hand side, what is this term? What is the right hand side term? We said if you look at here, the right hand side terms are Hi ui squared by 2 g z I and Pt omega I we have neglected. On the here Hi ui squared by g z I, but in a hydel power station this term is important. In a hydel power station this term is important. Therefore, this term we should take into account. That is why I said whenever we delete a term, we should be very careful. So, what I have done is that I have again looking back at this, I have put all the terms that are appropriate to a hydel power station. So, what does it look? What is Hi ui squared by 2 and then g z I, all that I have put in here. So, it looks like this. So, you have the effect, the left hand side is 0, the right hand side has the effect of pressure, and at position 0 and position 2 both are open to atmosphere. I have taken it as P 0. Both P 2 and P 0 are at the same pressure. So, I have knocked it out. I am doing a energy balance between position 0 and position 2. And what is Hi? I have taken it as C V T naught minus of T r. I could put C V or C P, both are not very different. Okay. And then you have, I have neglected this term U naught term, as not as very important. Therefore, you have G Z naught as the term here, and similarly you have G Z 2 at this here. So, what have we done? We have written the energy balance where the left hand side is 0, we have knocked out the pressure terms, we simply have what is called as a simplified form of the energy balance, which looks like this, which means the amount of energy that we produce per unit mass of flow is G times Z naught minus Z 2 and C V times T naught minus of T 2. Now, if T naught equal to T 2, then this term goes away, then the amount of power that you produce, if I have taken F as 4000, it is 2 megawatts. Okay. Is that clear? So, I have taken C V this term as 0. Suppose we find there is a small increase in temperature, small, I have taken as 0.005 or 0.005. It really depends upon how well you design the conduit leading from the reservoir to the hydel tub. So, you notice here that if you allow an increase of 0.05, you have lost more than 50% of the power. This is what I want you to appreciate. Our fluid mechanics, which designs this conduit from the reservoir to the hydel turbine, which might be several kilometers away. Okay. It may not be nearby. Okay. And the velocities, part of the reason why I have knocked out this term u naught, because velocity would be the same in both the places, that is why I have knocked it out. Okay. So, the point to remember here is that we can lose a large amount of energy by not taking care of the design of the conduits. That fluid mechanics is an important part of design. See, we all think that mechanical energy can be transmitted without loss of efficiency. We always think of Carnot inefficiency, but here is an instance of mechanical inefficiency which is as high as 50%. So, this care we should take in the design. So, let us see what happens in a steam turbine. Steam turbine we have done anyway. We already calculated steam turbine, we have calculated here. If you do the same calculation for a steam turbine, it is about minus 0.2, 0.63. Okay. So, we can calculate the flow work required for a steam turbine or for a sulfur dioxide plant and so on. Now, we also said that this is not common, but this is something that we would like to do, that we can apply our energy balance also to run what we call as a reacting system which will produce power. How do you make a reactive system produce power? That means a reaction like this 2NO2 times N2O4, this reaction, of course, reactions known to be instantaneous. Therefore, depending upon the free energy change of this reaction, there are two reactions, one is N2O4 going to NO2 or NO2 going to N2O4. So, you can see here. So, you can hear this picks up energy and then delivers energy, picks up energy, delivers energy. So, here it picks up energy at Q1 maybe at 80 degrees centigrade and then at Q2 at maybe at 25 degrees centigrade it delivers. So, it is Q1 minus of Q2 is the work produced if you can make it produce work. So, in some cases you are not able to produce work or you are able to use it for a space heating application. Since a lot of low temperature heat is available in many places, you can pick it up using a chemical reaction and deliver it to for space heating. So, the important point here is that there is tremendous scope for designing working fluids which is able to pick up heat at low temperature for space heating application. Otherwise, you will have to use more expensive materials. Here is an instance where so much of heat is available at this low temperature, which is required for space heating applications. So, reacting fluids and our energy balance is able to make use of all these, because the energy balance is written keeping in mind that the energy, what is our energy balance? Our energy balance only saying that d by dt of N I H I is F I H I and F I H I out, F I H I in. Basically, it is saying how much energy is coming in, how much energy is going out, how much heat you put in, how much work you take out. So, just to summarize, what we are saying is that you have an energy balance where the system has some amount of energy equal to amount of energy coming in, amount of energy going out plus Q minus W s. Just to put it in the context of a stirred vessel, what we have said is that H I system therefore, is also equal to H I out. Our nomenclature is that the intensive properties of the system is also equal to the intensive property of the exit stream. Therefore, I have denoted it as H I. Okay. And then I put a 0 to take care of input streams. So, in this equation I have written it slightly differently, taking into account the fact that H I in the system is same as H I in the exit stream, while H I and F I in the inlet stream has got a 0 here to indicate that it is an inlet stream. Okay. So, this is a statement of energy balance d by dt of N I H I summed over all species equal to summed over all species F I H I at inlet minus sigma F I H I at the outlet, no subscript plus Q minus W s. Now, our interest is to be able to put this whole equation in a form that we can use for our reacting systems. Let us see how to do this. To do this, what we have done here is that this term sigma N I H I d by dt, I am just separating it as two terms, N I d H I dt, H I d N I dt. The first term here N I d H I d by dt is written as two terms. Now, the advantage of doing this is that when you look at a single reaction, alpha 1 1 A 1 plus alpha 1 2 equal to alpha 1 and A n equal to 0, we recognize that the rate at which species A 1 reacts divided by the stoichiometric coefficient, rate at which species 2 reacts divided by stoichiometric coefficients equal to rate at which species n reacts divided by stoichiometric coefficient. So, all this equality equal to R 1, which we denote as the intensive rate of that reaction. So, if I ask you what is the rate at which component A 1 is getting formed, you will say that it is R 1 multiplied by alpha 1 1. What is the rate at which component A n is reacting? You will say it is R 1 multiplied by alpha 1 n. So, that is the nomenclature which you are doing. Therefore, our material balance in this stirred vessel for component I will look as input, output, generation. What is the generation term for component I? R 1 times alpha 1 I, because multiplied equal to d by dt of N I. Okay. So, our statement of material balance for component I. Okay. Now, our interest is what? Our interest is to see whether we can generate this term H I d N I by dt, because you can generate it from this by multiplying by H I and summing over all species. What is meant by multiplying by H I summing over all species? What is meant is, we write one equation f 1 0 f 1 minus f 1 r 1 alpha 1 1 v equal to d n 1 dt. That is one equation. Similarly, there are n equations. So, each of those equations you multiply by the appropriate species enthalpy and sum over all species. So, that is what, when you multiply it throughout and sum over all species, what you find is this. That means, if you multiply throughout by H I and sum over all species, what you get is sigma H I f I 0. Please note here, I am just multiplying by H I and summing over all species, correct. Multiplying by H I, summing over all species, then what I will get? H I f I 0, H I f I, and then the last term. So, what I have done here is, I have multiplied this by H I, therefore, it becomes H I f I 0, H I f I, and then I multiply this term by H I and summed over all species. Therefore, I get R 1 alpha 1 I H I v equal to H I d n I by dt and summed over all species. So, what have we done now? So, now we can simplify. What do you do now? Now, we have this equation here. So, we have this equation where H I d n I by dt we have generated here, we have generated. So, this we have generated using material balance. Okay. So, I can substitute for this term from this equation 4. Is that clear? So, we have generated this H I d n I by dt by looking at the material balance. Therefore, in this equation 3, you can replace H I d n I by dt by the left hand side of this equation. So, when you do that, what you find is this. So, I have put all the terms are written here. You find left hand side, right hand side, all the terms. You find it sort of some terms knock off, and we recognize that this term R 1 times alpha 1 I H I v is essentially R 1 times alpha 1 1 H 1 alpha 1 2 H 2 times alpha H n, which means what? This is the enthalpy change for reaction 1. So, this term becomes enthalpy change for reaction 1. Therefore, this whole term becomes N 1. So, how the energy balance looks like now is, it is N I d H I by dt, the first term. Second term H I f I 0, H I f I 0, H I not f I. So, you can combine these two terms, you get H I. So, what I get here is, you can see here the common thing here is what? I have a missed a term here, f I 0 should be f I 0, sorry. So, it simplifies as N I d H I by dt and f I naught from here. Can I see both? Okay. H I minus H I naught, and this term becomes R 1 times delta H 1 star, which is the enthalpy change for reaction, plus Q minus W s. So, now it is in a form which is a little easier for us to make use of. Even if, for example, suppose there is a reactor in which many streams are entering, and those streams might be entering at different temperatures, different quantities. All those effects can be appropriately accounted, because each stream coming at different temperatures, coming at different enthalpies. So, the form in which this equation is written helps you to manage various inputs into a reactor, various temperature input, all those kinds of things can be handled. For a special case, we can do a lot of simpler things. So, this term R 1 times V times delta H 1 star, this is what, this is for a single reaction. You can write this R 1 in terms of what is called as R 1 times alpha 1 k and divide this by alpha 1 k. What does this mean? This is rate of formation of component k multiplied by the enthalpy change expressed with respect to component k. This is how data is often available. So, what is important is to recognize this term and put it in forms that you and I can understand. R 1 times alpha 1 k refers to rate of formation of component k. This is often readily available, because we measure in our experiments, we will be measuring this term. Okay. So, then in that case you should multiply it by the rate of the heat of formation, enthalpy change for the reaction expressed with respect to that component. That is important, then only it will be consistent. So, in this form, the way in which this equation is written, it is probably the most general form in which you can write a chemical reactor energy balance. It takes into account all sorts of variations that might occur. Having said that, we recognize that this term H I can be put in terms of temperatures, because the enthalpies are available to us in terms of a standard heat of formation plus various C p delta T, which takes into account the effect of the specific heats. So, what we have said is that if there is no phase change, then clearly we do not have to account for phase change solid to liquid, liquid to gas, gas, all those things is not required. We simply can look at enthalpy at temperature T is standard heat of formation plus an integral which goes, which is the average specific heat in that interval between T and T r. So, we can express H I at T like this, H I at T 0 also like this. So, this is an assumption. What is this C p? This C p is the average in this range. This is the average. Okay. So, every time we look at this, we look at the average specific heat in the range T to T r and T to T naught. So, expressing our, looking back, if our equation here, where is our equation? So, this is our equation N I d H I. So, now I can replace H I in terms of temperature and specific heat. Therefore, this whole equation N I d H I by d t simplifies as something like this. So, first term is N I d H I, this is what we have written here. Let me just go through. This is N I, which is written as V I, this is V I. This is V I. Okay. So, N I is V I times C p I, correct? Is this clear? Please understand N I d H I by d t. N I is what? V I times C I. C I is missing, correct. Okay. I have written it here, I have written it properly here. So, the first term, let it stay like that, this is N I, let us no harm in that. So, N I C p I, this is written in this form V times C p I, C p means specific heat d t d t, similarly the right hand side. So, what have we done now? So, what we have done is that each of these terms H I and H I naught and H I, we have put in terms of specific heats. Therefore, the right hand side now looks in terms of V I C p I, this term C I C p I, the only term that has to be summed over all species is V I C p I. On the right hand side, the only term you have to sum is C I 0 C p I. In other words, what we have done is that by expressing the enthalpies in terms of specific heat, even those, if you look at this, H I naught and H I naught is known, H I changes depending upon the extent of reaction. Similarly, H I changes because of extent of reaction. But by this formulation of writing in terms of volumetric specific heat, what we have done is that C I C p I, C I changes, but C I C p I for a mixture does not change very much. Okay. In other words, a rather difficult problem we have converted into a simpler problem by combining C I C p I. So, that the left hand side now simply looks like a volumetric specific heat multiplied by the reactor volume d t d t. Why it has been possible? Because we have written this sigma C I C p I as a volumetric specific heat, which does not change during reaction. This is the assumption, and it is not a bad assumption. You can do calculations for several systems, you will find that sigma C I C p I for all the species taken together for the reaction may not have changed very much. Similarly, sigma C I 0 C p I summed over all species also would not have changed very much. So, it simplifies otherwise messy kind of system. The whole equation looks in this form V C p d t d t is V naught C p T naught minus F t. The assumption here is that all the feed stream is coming at T naught. See, in the previous formulation that assumption was not there, but now we have said all the streams are coming at T naught. So, this formulation is not useful when you have many streams coming in at different temperatures, but this formulation is very useful. So, what is important for you is to recognize that we must use the appropriate formulation for our application. Okay. So, we have this statement for a single reaction saying that R 1 V, this is heat generation if it is an exothermic reaction, or heat absorption if it is an endothermic reaction, heat added, work output. Typically, this may not be important in many cases, because we are not trying to most cases, but it may be important in some, and appropriately you will have to delete terms that are relevant to your application. Okay. Now, if we go from a single reaction to a multiple reaction. So, what do? We had only one reaction here, correct. Now, we have many reactions. In other words, how do you go from a single reaction to multiple reaction? So, what we have done for that case is that the left hand side we had there was one term on the left hand side was sigma Ni dhi by dt, Hi dni by dt, which we did some manipulation. We can do the same here. How do we do the same here? We recognize that we have p reactions alpha 1 A 1 to alpha 1 n, similarly alpha p 1 A 1 to alpha p 2. There are p such reactions which are taking place in our stirred vessels. So, what we want to do is that we want to generate what is this term Hi dni by dt for the case of multiple reactions. How do we do that? We do that by writing the energy the material balance for the ith species input output. The generation is because of R 1 alpha 1 I, R 2 alpha 2 I, R p alpha p I. Notice that all the rate processes appear in the generation term multiplied by V equal to 0. So, this is the statement of energy material balance, and we want this term Hi dni by dt, which means what? We have to multiply this by Hi and sum over all species. So, let me say it once again. What we are saying here is that when we have a multiple reaction, this term Hi dni by dt we want to replace from energy material balance, and we do that by writing the stoichiometry, writing the energy material balance for species I, which is what f I naught minus of f I plus the generation from all the p species R 1 alpha 1 I, R 2 alpha 2 I, R p alpha p I. Okay. So, now we can multiply by Hi and sum over all species. Okay. Once you do that, we can generate this term. Okay. That is what. So, when you do that, and it sort of simplifies nicely. So, we need not go through this, but when you do that, the whole thing simplifies like this, that this equation, that means this, which means this term for a multiple reaction, when I substitute, it looks like this. What we have done is that the second term Hi dni by dt, which is substituted from material balance, and then the whole equation looks something like this. So, only change that has taken place is that wherever this reaction term occurs, in the reaction term previously there was one reaction, now there are p reactions. So, this term now becomes j equal to 1 to p R j delta H j star V. So, this term the heat generation or heat absorption, previously it was because of only one reaction, we had only one reaction, correct, and now we have p reactions. Therefore, this term becomes R j alpha j, that is what it becomes. So, it becomes R j multiplied by the heat of enthalpy formation, enthalpy change for formation of the jth reaction, j going from 1 to p. So, the energy balance for a single reaction or multiple reaction, it does not really matter, because the form is identical, the form is identical. Okay. So, now we can replace everything in terms of temperature. When you do that, if all the feed stream is at T naught, this is how the equation looks like. Why is the summation over I equal to 1 to n? This is here now this term alpha 1 I H I, we have replaced it as delta H I star, which H 1 star. See, this is for single reaction. This term, the important thing is that this term is actually delta H 1 star for single reaction. Now, when there are many reactions, then it will become, for jth reaction it will become delta H j star. R j is the intensive rate of formation or intensive rate of that reaction j. So, R j, there was j going from 1 to p, there are p processes, rate processes, is that clear? So, all the feed is coming at same temperature, this is the assumption, but in this form it is not so bad, because that effect is there. So, here in this form you can deal with different components coming at different temperatures, but from this point to this point all the components are coming at same temperature. So, whether you use this or use this depends upon what is the application you are looking at, that you should take care. Whether it is single reaction, multiple reaction, when there is one reaction, then you j going from 1 to 1. Okay. So, this form equation 4 is a very general statement of energy balance for a stirred vessel, where VCP, which is volumetric specific heat, rate of change of temperature of the system equal to V naught Cp T naught minus of T is the flow term, this is the reaction term, heat addition and work. Okay. So, this is how it looks. If I ask you, for example, suppose we have an instance of a multiple reaction taking place in a, let us say, a stirred vessel where the temperature is maintained constant. It is still as in the sense what I am saying is that there is an instance, let us say you have an equipment which is into which fields are coming, but nothing is going out. What are we saying? V naught is finite, but there is nothing going out. Now, the way this equation is written, the V naught is finite, but nothing is going out. So, people tend to think that this second term should not be there, but second term is coming because of H I. What is H I? It is the enthalpy of the stream in the equipment. You understand? So, we have typically we think the second term should be removed, but no, this is the important point, and I have seen many instances where people knock out the second term. This is within the H I is what? H I is the enthalpy of stream in the equipment. So, see, it is multiplied by V naught, not V naught is input, not output. Is that clear? So, you should be very careful in a given exercise, the equations how they play out in your application, you have to be very careful. Otherwise, you might knock out terms which are actually not appropriate to be knocked out. Okay. And I thought we did some exercises where I pointed this out to you also. Okay. In one exercise, some of you said that no, we should knock it out, and then we look back at the equation and realize that no, we cannot knock it out. Okay. That is in semi batch you will find these kinds of problems. Now, let us look at the same problem for the case of a plug flow vessel. We looked at stirred vessel, we look at plug flow vessels. What is a plug flow vessel? A plug flow vessel is one in which there is no mechanical stirring. So, we have here a vessel into which fluids are coming in, fluid is coming in, fluid is going out. Okay. And our material balance is for this differential element. So, what is the statement of energy balance? Input of energy minus the output of energy plus Q, which is the heat input per unit volume. Therefore, I multiplied small q by delta V, and then W s times is the heat work output per unit volume. So, input, output, generation, there is no generation. This is heat input, work output equal to 0 for steady state. We are writing the material balance for steady state. We have not had time to look at the unsteady state yet, but okay. So, in the limit as delta V tends to 0, the general material energy balance for a plug flow vessel looks like this. This is the, so d by dV of F I H I becomes Q minus W s. Okay. Now, d by dV of H I F I is what we have to deal with and put it in appropriate forms, so that we can see what happens to temperature of the equipment. For that, what we have done, we know that we can expand this as F I d H I dV and H I d F I dV, and our material balance equation tells us what is d F I dV. So, if you look at d F I dV, how does it look? d F I dV due to is equal to rate of generation of component I. What is rate of generation of component I? R 1 alpha 1 I up to R p alpha p I. So, d F I dV in terms of all the species, therefore, when you multiply by H I and sum over all species, H I d F I dV becomes sigma R 1 alpha 1 I H I. What is this? We know this is heat of enthalpy change for reaction 1 alpha 1 I H I. Alpha 2 I H I is enthalpy change for reaction 2. Alpha R p I H I is enthalpy change for reaction P. Therefore, this term, this whole term H I d F I by d V, what we have done is that this, if you recall here you are, this is F I d H I d V, H I d F I d V. Therefore, the term H I d F I d V you can now replace from here, correct. So, what I have done is, so this equation here, this equation I have written it as F I d H I d V plus H I d F I d V. This is what I have written. I have written it again here. Okay. So, our equation 1 I have written it by expanding the term Fi dhi dV. Okay. So, I have written it in this form, two terms are appearing. This Hi dFi dV can be substituted from here, which is what R 1 delta H 1 star, R 2 delta H 1 star, R p delta H p star. Therefore, this term becomes R 1 delta H 1 star, R 2 delta H 2 star, similarly up to R p delta H p star. Therefore, our energy balance now becomes Fi dhi dV plus all these R 1 delta H 1 R 2 to R p equal to Q minus W s. So, this if you take it to the other side, it becomes this Fi dhi dV putting in terms of our volumetric specific heat becomes volumetric flow times volumetric specific heat, that sigma C I C p I dt dV. This term is simply summation over j equal to 1 to p. There are p rate processes here plus. Okay, I have taken it to the other side, therefore, I put a negative sign. This is taken to the other side, so negative sign plus Q minus W s. So, for a plug flow vessel where there is no stirring, we find that V c p dt dV, which is the accumulation per unit volume. Okay. This is V c p dt dV. This is the rate of change of temperature of the equipment, and this is the rate of heat generation if it is an exothermic reaction. This is heat input, this is work output. The only thing, the difference between a stirred vessel and a plug flow vessel, here Q is heat input per unit volume. It is per unit volume. Okay. That is the difference. It is not heat input per unit time. In the previous case, it was heat input per unit time. Okay. So, that is the difference that we should take care. All right. Now, let us see what simplifications we can do. This term Q, heat input per unit volume, assuming that our equipment is a pipe or a tube. So, tube surface area, see the volume of a pipe, I have just calculated here, our heat transfer is H, heat transfer coefficient, surface area multiplied by the driving force. Therefore, if you have a unit volume here, suppose this is how the heat is coming in like this, coming like this. This heat per unit volume I have written where A h is the heat transfer surface per unit volume. What is A h? It is heat transfer surface per unit volume. For a pipe, what is it equal to? Surface area divided by volume of the pipe, which is 4 by d. Or in other words, this A h for a pipe is 4 by d. Therefore, small q for a pipe is actually 4 h by d T c minus of c. Understand? Therefore, energy balance for a pipe looks V c p dt dV summation over all p rate processes plus 4 h by d times minus W s. This may turn out to be typically 0. It may not be, I am saying it may turn out to be, it may not be. But what are we saying now? See, we are saying that in a plug flow vessel, the rate of change of temperature with volume is heat, if it is exothermic, it is heat generation, and this is per unit volume per unit time. You can see this per unit volume per unit time, plus what is the heat that is removed by, see what is this T c, T c minus of T? This is the heat that is added to the system. Okay. Typically, we will find this term is negative, because you will remove heat. Therefore, T c minus T will be negative. So, you will find this will be positive. So, this is a positive term typically for an exothermic reaction. Okay. This turns out to be a negative term. Okay. Therefore, this positive and this negative, when they balance each other, then it had to be the hot spot or the point of maxima in the profile, temperature profile. The point of maxima in the temperature profile occurs at a point where the heat removal becomes equal to the heat generation. Then this becomes 0. See, this is negative, this is positive, therefore, this becomes 0. The point at which where it becomes 0 is the point of maxima. Now, the interesting thing that is of relevance to us is, generally we like to see that the temperature at which the maxima occurs is within the allowable limits of the material of construction, and more importantly allowable limits of the catalyst that you may be using. In most of the cases, it is that catalyst which is crucial to ensuring that this temperature never goes beyond what is permissible. So, what you would do is that you would like to see that this, when it goes to 0, what is the temperature at which this equality take place, and what is the temperature for a given choice of pipe size. For a given choice of size of the pipe, you will see what is this temperature, whether that temperature is good enough for the catalyst to be acceptable. Now, what you will do is that frequently when this pipe is large, you will find that this temperature becomes unacceptable. So, you will find that the choice of pipe size or the size that you will choose will be determined by the hotspot temperature your system will permit. So, this calculation you will do to find out what is the best temperature, best choice of pipe size that you can use. When you use a small pipe, because it occurs in the denominator, the heat transfer is very large. So, it is able to dissipate heat very fast when you use a small pipe. When you use a large pipe, it is not able to dissipate heat very fast, and therefore, the hotspot temperature goes up. You understand? So, in this, when you solve this equation, these are the points that is of greatly important to us. What is the choice of D, so that this temperature is what you would like to see? Or in other words, when you do your numerical calculation, what you will do? You will choose different pipe sizes and you will generate this hotspot profile and see what is the profile that is acceptable to you. And you will choose that profile which is acceptable to you, or that pipe size which is acceptable to you. Okay. Is this clear? So, this is the most important point as far as the design of tubular reactors are concerned. You will find in many cases, we would like to operate it adiabatically. That means, this Q is 0. There are many instances, particularly if you go to an ammonia plant or sulfur dioxide plant, it is an adiabatic operation. Why is adiabatic operation? That means, we set this equal to 0, that means, you allow this temperature to rise. You allow this temperature to rise, but you do not allow it to rise beyond a point. Or in other words, you have a very short bed, the bed is very short. Allow the temperature to rise and you cool. You understand? So, that is the idea of you allow the temperature to rise, you cool, allow the temperature to rise, you cool, allow the temperature to rise, you cool. So, that you are able to reach the extent to which you want to reach. Okay. So, all those strategies are built into this equation now, because you will write this equation for every reactor. There are 7 reactors, you will write it for every reactor. So, all those are integrated into this statement of energy balance. Now, there are people who talk about what is called as radial flow reactors. What is radial flow? You can have flow outwards or inwards. So, now you will find the way this is formulated, you can take into account radial flow quite comfortably, but here you should change this, because this is for a pipe, this we have written for a pipe. So, for a radial flow reactor you will change this AH you will change for a radial flow. Okay. So, what I am trying to point across is that, see, whatever simplification that we make, it is under the assumption that we are using a pipe, but moment it is not a pipe, then the left hand side is formulated properly, but the right hand side is not satisfactory. So, you should formulate this 4 H by D, which is for a pipe, for a radial flow reactor, then it becomes appropriate for the radial flow reactor. So, what in other words, what we are trying to point out here is that the equations are written in a fairly general form, so that you can use it for the design that is appropriate to your application. What is important is to replace those terms which are not appropriate, so that it applies to your situation appropriately. That clear what we are saying? So, whether it is a stirred vessel, we had in a stirred vessel we had generation of energy term, we had a heat transfer term, we had work term, okay. And there we did not have this kind of problems. Okay. But here in tubular reactor, because there is no mixing, we have these new features, for which you have to appropriate choice of pipe sizes are required. And much of tubular reactor design that you will see in the process industry, a great deal of effort is spent in trying to make a good choice of the size of the pipe. It is important. I will stop there today.